9.4, the integral. We learned earlier in this unit that to find the accumulation given the rate, how fast something is changing, we can find the area under the curve. To approximate, to guess the area under the curve, we can use a Riemann sum. For example, the right Riemann sum says we're going to find the sum of our interval times f of the right hand point. For example, for this function, which is f of x equals x squared, it's going to be, each interval is 1, so it's going to be 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3. We can write this in summation notation. So I equals 1 to n, where n is the number of intervals. The delta x here, that's how far each one is for each of the intervals. If we're going from 0 to 3 and we have 3 intervals, then delta x is 1. And then this point is f of 1. This point is f of 2. This point is f of 3. Okay. But as we can see from this graph, the right Riemann sum is just an approximation. The area is not equal to the exact area under the curve. But what would happen if we have more and more intervals? In this animated GIF, in this animation, we see that here, as we get closer to 100 intervals, we get to the area under the curve. But right now, when R1, as we can see, the more intervals we make, the closer it gets. The number here, R, that's how many intervals we make. This is the right-hand sum. As the number of intervals increases, our answer gets closer and closer and closer to the exact area under the curve. So we can take the right Riemann sum, the sum of I equals 1 to n of delta x times fx, and take the limit as n goes to infinity, the infinite number of intervals. Each interval is going to be infinitesimally small because the interval is b minus a over n. When we do that, this squiggly line is called an integral. We can call this the integral from a to b of f of x dx. This is called the integral. Okay. The integral is the limit when we have infinite number of subintervals, so it's equal to the area under the curve. For example, we want to write an expression that can be used to find this area, the exact area under the graph of f of x equals x squared for the interval 1 is less than x is less than 3. So we can write an integral like this. That's the integral. We want f of x dx because this is f of x and the size of the interval is dx. Okay. And we're going from 1 to 3, so we will write 1, 2, 3. Okay. Of course, that's just equal to 1 to 3 of x squared dx. Okay, so that's an interval. In the next 2 lessons, we will learn how to calculate these integrals.